Okay, so we're going to take a brief aside here and talk about something called the Cook Snowflake. Maybe it's Koch. I'm not sure. I think he was a Swedish mathematician. Not sure exactly how to pronounce that, but I think it's Cook. Anyways, we'll call it the Cook Snowflake. We're starting out with an equilateral triangle, so pretty basic figure. But here's what we're going to do. At each stage, we're going to kind of bump this out a little bit. So we're going to add a little bit to each side of the triangle. So there's like our first stage. So what do? We added a little segment here, a little segment here. So we're adding more little equilateral triangles. Let's look at the next stage. And it's getting more convoluted. And the next stage after that. And after this, it's really tough to see the changes, right? Because they're getting really, really small. The Cook Snowflake has a lot of different properties. And they're kind of neat and strange and counterintuitive in various ways. So here's a better rendition of that. And it's actually pretty nice because it's on Wikipedia. Wikipedia is actually pretty awesome sometimes. Even better than that, let's zoom in a little bit. And here, this is what it would look like if you had a microscope and could keep on zooming in and zooming in and zooming in. And you see what's called a fractal shape to this, a self-similar pattern that no matter how much you zoom in, it looks like the original image. So it's pretty cool. Now let's do a little bit more with the Cook Snowflake here. So here's Cook, and some of this is kind of a note for me because I want to look up some more about his prime number theorem, or his work with the prime number theorem. There's a few things I want to look at. The first one is the area of the Cook Snowflake. What's that going to be? And part of it is a little bit of work with stuff that we've already done. Here's your summation notation. You start out with the area of that original triangle, whatever it is. And then each time you add more sides, you're adding more to the area. So that's this term. You don't have to follow all the math here. I'm not going to explain all the math. But this is a geometric series. And we have formulas that allow us to calculate that. So we get this. And finally, if you clean up this expression a little bit, you get a sub 0 over 5 times all this mess. That's the area of this thing at any particular stage. So a sub 0 is just the area of the original triangle. And then capital A sub n is the area at the end stage. So what happens as n goes to infinity? Well, something nice happens. Let's think about this term. It's less than 1. Now think about an easier number, like 1/2. If you took 1/2 and then squared it, or 1/2 to the third power, 1/2 to the fourth power, what's going to happen? 1/2, 1/4, 1/8, 1/16. It's closer and closer to 0. In fact, that's exactly what this thing does, is it goes to 0. So if that goes to 0, then all that's left is the 8/5 times a sub 0 over 5. So wow, we've got a nice expression for that. Now, generally speaking, when people work with triangles, equilateral triangles, there's a formula for the area of equilateral triangle. In terms of the sides, it's square root of s, or square root of 3 over 4 times s squared. If you put that in, there's the area of your Cook Snowflake. Boy, nice closed form expression. But here's the bizarre part, or the start of the bizarre part. What if you looked at the length of the sides? Okay, all right. So first iteration, or the 0th iteration, you have a length of whatever side, length s. Then the next one is 4/3 times that, and then 4/3 times that again. And so basically you get a length of the side that looks like this. The difference here, though, is this limit. 4 over 3 is bigger than 1. So as n goes to infinity, where is this limit going to? Infinity. That's bizarre. So you've got something that has a finite area. We calculated the area, but yet it's infinitely long. So it's really, really, really convoluted shape. So in summary, it's got a finite area, but it's got an infinitely long perimeter. Let's think about something else. even though it's continuous everywhere, let's look back at one of the pictures. It's continuous everywhere, right? But what can you tell me about the derivative of the function right at this point? Doesn't exist, right? Because it's a corner point. So it's continuous everywhere, but in the limit, when you finish forming that, it's differentiable nowhere. It's changing so fast that even though it's continuous everywhere, it's differentiable nowhere. Now, a couple other things. I mentioned that this is a fractal. Fractals are pretty cool shapes. You'll see them in nature all the time. It's a different type of geometry to describe things like clouds, like the bifurcation of blood vessels in your body, etc. So they're pretty cool. It has a fractal dimension of 1.26. So I'm not going to explain much about that, but there are applications and stunning things about even your own body that you can understand with fractals. Let's start with your lungs. And that's really the only example I can give you is your lungs. The lungs are amazing because they have an incredible amount of surface area. You can describe your lungs with fractal geometry, not with regular geometry, not the Euclidean geometry that you grew up with. How much surface area do you think you would have in your lungs if you were to flatten them all out, spread them all out? Now, don't do this while you're using them, okay? All right. But if you're to flatten them all out, how much surface area do you think you'd have? Awful lot. In fact, I think I'm not the first one to ask this because Google had an answer ready for me right away when I typed it in. About 80 square meters, about the size of half of a tennis court if you flatten them all out. That's just amazing. Just an amazing amount of area for your lungs. So, anyways, there you go. So a little bit about fractals, Cook Snowflake, and a little bonus stuff there.